Hi everyone, I am Ozgur from Boğaziçi University. Today I'm going to present our work, ISNAS-DIP, Image-Specific Neural Architecture Search for Deep Image Prior. So let's begin. Image restoration is the task of recovering the original image from its corrupted version. Traditional algorithms offer supervised approaches to this task. However, the ground truth labels are not always available to learn such a mapping for a given domain, which limits the use of approaches under supervised settings. To tackle that problem, researchers have investigated unsupervised approaches, and they come up with a new idea, deep image prior. The video illustration shows the generated images and their PSNR values along iterations for an image denoising task with deep image prior. It has an advantage over supervised approaches, since it works solidly with the corrupted image and can produce competitive results for image restoration tasks without a supervised training phase. However, the design of the architecture is strongly affecting the quality of the restored image. Leveraging this insight, NAS-DIP proposed the reinforcement learning-based neural architecture search to improve the deep image prior quality and offer the novel search space for image restoration. One of the major drawbacks of this approach is its computational expense, since numerous networks need to be evaluated before determining the best model. Moreover, it searches a single architecture for a given restoration task, but doesn't take the effect of the image into consideration. We first motivate image-specific neural architecture search by showing that, in a given search space, there is only a small overlap of the best architectures for different images. This is illustrated in the figure, where the numerical values in the matrices show the number of overlaps between the top 10 models for each image for denoising on the left and inpainting on the right. We then propose novel metrics to find optimal architectures with minimal training. To identify architectures that are fitting for a specific image, first, we propose image-dependent metrics. They measure the difference between the power spectral densities of the generated initial output and the corrupted image. The intuition relies on the fact that the more these two are similar, the better the model will reconstruct the image, since it will be closer to the solution space. Second, we propose an image-independent metric to measure the low-pass characteristic of a CNN. This allows us to dissect whether the contribution is due to using the PST of the CNN-generated image or the image dependency of the matrix. Given any search space, the ISNAS-DIP algorithm works as follows. For each corrupted image to be restored, first we sample m randomly initialized CNN models from the given search space. Then we calculate the chosen metric for each model. After, we sort the models based on their metric values and select the top n1. Then the problem turns out to performing a selection given a small cohort of models. To perform a selection, we optimize these n models and obtain their outputs. Then average those outputs and select the model whose output is closest to the average. To expedite the final selection process, we propose a second selection method by resizing the corrupted image while optimizing the n models. Moreover, we have generated and released a publicly available neural architecture search dataset for deep image prior. Within this dataset, 522 models from the same search space are optimized under deep image prior procedure for image denoising and image inpainting tasks. All of the training history is provided in this dataset. This benchmark allows researchers to evaluate their NAS algorithms for deep image prior framework. We tested our algorithm on NAS dataset for DIP. This figure shows the distribution of the final PSNR scores of the 522 models for both image denoising and image inpainting. We observed that the selected model by PSLDB strip MSE metric with n is equal to 15 is always located on the right side of the peak value for all images, which is depicted with red color. In addition, the black bin shows the same score when n is equal to 5 case. It indicates that this metric has the potential to reduce the size of the search space into only a few models. Furthermore, we compared our algorithm with the state-of-the-art approaches on conventional datasets. In this table, we report the PSNR scores of the DIP, NAS-DIP, and our metrics. We employ full-sized averaging selection among 15 models for our metrics. For denoising, PSTDB strip MSE metric, and for inpainting, PSTDB MSE metric takes the first place for all datasets. Summarily, in this work, we show that the performance of the deep image prior is image dependent. Based on this insight, we proposed several metrics and show that our algorithm outperforms benchmark architectures for image restoration tasks using deep image prior. Furthermore, we establish a NAS dataset for DIP that can be used for future research. Thank you for watching our presentation.